Hello everyone, welcome to tutorial 11. So today we will be going through our notebook. So fine tuning Llama with QLoRA. So this Jupyter notebook demonstrates how to fine tune Llama using QLoRA. So it is quantized LoRa, which allows fine tuning with a 4-bit quantization while maintaining high performance. So I encourage everyone to go through the paper of QLoRA. QLoRA is basically efficient fine tuning for quantized LLMs. So basically what the paper, the innovations, there are 3 innovations of this from this paper. So basically they introduce a 4-bit normal float, a new data type that is information theoretically optimal for normally distributed weights. Then we have double quantization to reduce the average footprint by quantizing the quantization constants, and 3 is paged optimizer to manage memory spikes. So as we will go through over this LoRa concept with the help of this notebook, and for this notebook we will use transformers, the PEFT library, and bits and bytes library that that has all the capabilities of this LoRa and QLoRA concepts. So what is QLoRA? QLoRA is an extended version of LoRa which works by quantizing the precision of weight parameters in the pre-trained LLM to 4-bit precision. So the weights, the pre-trained weights of LLM are basically in float 32, and then we need to quantize this float 32 into this 4-bit format. So typically the parameters are stored in 32-bit format, but QLoRA compresses them into a 4-bit format. What this basically does is it reduces the memory footprint, making it possible to fine tune on a single consumer GPU. So this method significantly reduces memory footprint, making it feasible to run LLMs on a less powerful hardware, including consumer GPUs like 4090, 3080 and so on and so forth. So with this, with the paper, I also encourage everyone to go through this democratizing foundation models via k-bit quantization. The video is from Tim Detmers, the author of the QLoRA paper and even the LoRa paper. It's a very nice talk. It's a long 1-hour talk, engaging talk. Please visit this. You will gain much more intuition into why this QLoRA works and why quantizing into the 4-bit format, where we are coming from 32-bit precision to a 4-bit precision, and even then we are not actually losing on performance. How is this possible? And even if you go through the paper, so this is the mean zero-shot accuracy on Vinogrande, Helaswag, Pika, ArcAZ and ArcChallenge using Llama models with a different 4-bit data types. So these are all 4-bit Llamas. So which is data type is float, data type is normal float, and then we have normal float and dequantization. Now what is dequantization? We would go through, but as you can see, although it's a floating 4-bit precision, as you can see, the green line, it is much higher than the floating point accuracy. The mean zero-shot accuracy is much higher. So why is this? How is this happening? Let's go through the notebook. And also I have pasted a link to a small QLoRA paper. I explained, this is a small YouTube video which you can go through, just in a brief what is happening in the QLoRA. So the key innovations is 4-bit normal float, NF4, which is a short form for NF4. is basically a data type specifically designed for AI applications, particularly in the context of quantizing weights of the neural network to reduce the memory footprint significantly while attempting to maintain the performance. So NF4 is theoretically optimal for data that has normal distribution, which is a common feature of neural network weights. So the weights of the neural network so when we are pre-training a neural network, so after pre-training phase, the weights are in some sort of a normal distribution in floating point 32, right? So and which is a common feature in neural network weights and can represent these weights more accurately than a standard 4-bit floating would. So when we are converting it to, let us say, 4-bit, but it is not 4-bit in float, it is a 4-bit in normal float, which is a new floating point, a new data type like our int 16, int 8, float 16, and so on and so forth. So for this 4-bit normal float, we have 4-bit normal float quantization. Is a method that is efficiently quantize the weights of a neural network into 4-bit format. Then we have blockwise k-bit quantization. What it does is basically blockwise quantization divides the input tensors into small blocks and quantize each block independently, which reduces the problem of the outlier. So in this process, we split the input tensor into chunks, and each chunk is quantized independently, with each having its own quantization constant. So let's say we have we divide, so we are going from a floating point, so it is basically -8 to +7, and we divide this range into 3 blocks, right, and 3 blocks. So then each of the blocks will be quantized independently, and each of the blocks will have an independent quantization constant. So with the help of this, the outliers we get, so even with outliers we get much higher precision, much higher quantization precision and stability with blockwise k-bit quantization by confining outliers to blocks. So we divided into blocks. So in the paper they use 64 blocks. So each outlier that might be there in the data, each outlier weight that might be there will be quantized independently of how the other weights are being quantized. So we get a higher quantization precision when we have this blockwise quantization, and each of the quantization blocks have several different quantization constants. So with this we also have double quantization. So double quantization is the process of quantizing the quantization constants for additional memory savings. So we have these quantization constants. Now we need to quantize these quantization constants also, so for additional memory savings. So while a small block size is required for precise 4-bit quantization, so small block size is required to have a precise 4-bit quantization. It also has, but this quantization constant also has memory overhead. For example, using 32-bit constants and a block size of 64 for weight, quantization constants add up to 0.0, so half a bit per parameter on average is the weight. So double quantization helps to reduce this 0.5 bits per parameter, that is on average, to double quantization helps to reduce this. Now on top of it we have paged optimizer. So let's say Adam. So the concept of paged optimizer is used to manage memory usage during training of these large LLMs. So this concept is similar to what we have paging in OS. So when training large models with billions of parameters, GPUs run out of memory. So paged optimizers are used to address these memory spikes during model training. So let's say a set of optimizer states, when that they will not be used, they are transferred to the CPU instead of the GPU, so that GPU portion that is held by the optimizer state that is not currently being used right now can be used for other purposes, for other GPU usages. Now, as we have seen in the last LoRa lecture, LoRa tutorial, the hidden state, the forward pass looks something like this, where we have h equal to w0 naught, which is the weight of the pretend weight that is frozen of the pretend LLM, x is the input, and then we have extra weights, the LoRa weights, which are again decomposed into B and A, two small matrices with the x. So, this can be correlated with QLoRA. So, as you can see, the YBF16, so this BF16 is the input. So, input is in a floating point 16, and XBF16, then we have a double quant where weights are in NF4, normal floating point, this normal 4-bit normal float. So, what so the floating point, so the weights are, the pretend weights are transferred to normal floating point, and then during the computation of the gradients they are again dequantized. So, double dequantized when with the weights. So, first there are floating point weights that are getting quantized to NF4, then when we are computing the gradients are again dequantized into let us say BF16, floating point 16, and then the operation is performed. So, as you can see, we have double dequant C1 FP32, C2 that is k bit, these are the quantization constants, and XBF is the input that is in floating point 16. Now, what does this double dequant mean? Double dequant is the first we do the dequantization of the constants, and then we do the dequantization of the 4-bit normal float that was stored in the GPU to floating point 16 when we are doing a forward pass, right. So, let us move ahead and install. So, we will use transformers, torch, PEFT and accelerate, and we will also use the bits and bytes library. So, bits and bytes library, let me show you. So, this is the official repo of bits and bytes. This now has been integrated to Hugging Face. So, bits and bytes is a lightweight Python wrapper around CUDA custom functions, in particular 8-bit optimizer, matrix multiplication and 4-bit 8-bit quantization functions. So, this has been migrated and integrated with Hugging Face, and please go through the docs and please go through the docs whenever required. So, this will install the required libraries, this will install the bits and bytes. After that, we will import, so auto model for causal LM, since we would be using llama. So, you would be using auto model for causal LM, auto tokenizer, training arguments, trainer, and since we are going to use the QLoRA, we would import LoRa config, get peft model and task type from peft, and bits and bytes for this QLoRA fine tuning. Now, we would be using alpaca dataset that is from Stanford, and for this demonstration we would take only the first 1000 examples. Let me show you the alpaca dataset. So, this is the alpaca repo, that is so this not, yeah, this. So, this is the alpaca models and how to generate the alpaca dataset. So, they for fine tuning, so Stanford alpaca, this is one of the first instruction following llama model. They have a 52K data that was, they have open sourced the 52K data that was fine tuning the code for then they generate new data with the model, and so on and so forth. So they contain so this data contains 52K instruction following data that is used for fine tuning the alpaca model. The data looks something like this, like below is an instruction that describes the task and blah 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 instructions. Then we have a prompt like instructions input and what's the response of the model, right? So this is the data, as you can see, like generate, rewrite, create, write, explain, and so on and so forth. And then we have more fine grained task with inside the data, 52K data. So this will require your Hugging Face token. This will be yours. This is a random token. This has to be replaced by your Hugging Face token, because this llama 27 billion, this is a gated repo and needs to be accessed via login. And we would pass in the bits and bytes config as something like this, like load in 8-bit true, bnb compute type is torch.float. So this is the compute type, like when we are doing the forward pass. So when we are computing the gradients, what would that be? That is in torch float 16. Then we have the device map to auto. Then we initialize the LM with llama, and which downloads the models and so on and so forth. Now these steps we have seen so many times in the tutorials, like so this is downloading the model. Then we have the tokenizer. Then we have a small preprocessed function like instruction text response for texting instructions, which tokenizes the inputs and the labels, and we generate like this. Then we tokenize the datasets via the map function with inside the preprocessed function and batching equals to true. This is how we define the LoRa config, like a task equal to causal LM, because it's a decoder only model. Inference mode is false. The rank of the small A and B matrices is 64. This is stability parameter of LoRa, and this is the dropout that we would be use. And this is the target modules that we would like to, have the LoRa weights. So QProj and VProj of the llama architecture will have the LoRa weights, and the weights other than this will have the full fine tuning. So now we are, so this model is downloading. I think it will be downloaded in a sec. Yeah, so it's done. Then loading the checkpoint shards onto the GPU. So this is how we apply the QLoRa model onto the QLoRa config onto the model. So this loading checkpoint shards is taking a bit of time, and this is how, again, we have seen so many lectures on Hugging Face. This is how the training arguments are passed to the training args, like the output DIR, the evaluation strategy, learning rate, batch size, number of epochs, weight decay, and safe strategy. Now then again we initialize the trainer with the model arguments, the tokenized train dataset. So remember to pass in here the tokenized train dataset and not the train dataset as it is. And then after that we so this is required if you want to visualize your logs, your loss functions, your metrics that you want to track, your grad norm, the gradient normalizations signals. So this is quite handy of a tool, weights and biases, or if you also can use TensorBoard and so on and so forth to check if there are spikes in your losses, if there are spikes in your gradients and so on and so forth, so that you need the training is not stabilized. The training has to be stabilized, then it's not stable. Basically the training is not stable if the loss function is the loss is getting up and down, and so you need to look into the model, and where there is some kind of data leakage, or some, so it's done, or there might be some issue with normalization, so that you need to renormalize your weights after certain layers. So, for this demonstration we are setting the mode of weights and biases to disabled, and by now you know that when we call trainer.train, it starts training the model, as you can see. So, we have 1200 steps, and it will take around 32 minutes to train, and this save pretrained will save your pretrained model, so that you can use in your later purposes, later usage. So, I encourage everyone to go through this QLoRA paper. This is an important, very important, very important innovation for this era, for this fine tuning of this large LLMs. You can't fit in this large LLMs in GPU. Let us say if you want to fully fine tune a 65 billion llama model, you would require around how many 10, 12 A100s, 12, 10 A40s, sorry. But now using QLoRA, you can just fit the whole 65 billion model in one consumer GPU. That's very handy, and the research they have experimented with a whole lot, heavily experimented paper. They have whole lot of ablation studies, like where the model is failing, where it is passing, and so on and so forth. So I encourage everyone to go through the paper, so that you know what this QLoRA is doing. You should understand QLoRA from ground up. This video helped me a lot. The team Detmer's slides are pretty good, and it's very intuitive. Please watch it. That's all for today. Thank you.